So this video is about computing in scientific notation, and this first example says that $1 bill is 0.00, let me make sure I get the right amount of zeros, 0.0001 meters thick. And then how many meters tall would a stack of $4 trillion be? Alright, and we're going to answer in scientific notation, and for reference, $1 trillion equals 10 to the 12th. So what we're going to do over here, we kind of have this problem set up already. So we'll set up a simple ratio of $1, and $1 is 0.0001 meters thick. And so this is our simple ratio that we're going to start with. So if we're going to rewrite this in scientific notation, it might make it a little easier. So if we're looking at this, as long as you remember that in scientific notation, only the first significant figure has a decimal. So whatever the number is, if it's 1.0 or 2.5, there's always only one figure. So if we have 0.0001 meters, then we can look at this as, since it's only going to have one figure here after decimals, it's going to look something like this. So it's going to be 1.0 times 10 to the something. So if we have the decimal here and it ends up over here, then what we're going to do is we're going to say that this decimal moves 1, so it moves 1, 2, 3, 4 times. And it's moving in the negative direction. So since this number is really small, that means that this scientific notation is going to be negative. It's going to have a negative exponent. Now if this figure had a positive, like 10 to the positive 4, then that would be saying that the number would be 1, and then this decimal right here, and then instead of moving to the left 4 places, it's going to move to the right 4 places. So this number would have 4 zeros and a 1, so that would be a very large number. That would be 10,000 versus, I don't know, whatever small number that is. Small. Okay, so we see over here 1.0 times 10, and we discovered that this is going to be -4 meters. Okay, and then the second part of the problem says that we are given a stack of what? 4 trillion $1 bills, and a trillion is 10 to the 12th. Okay, so we're given a stack of dollar bills, and we're asked to see how many meters that would be. So if we've done some proportions and ratios already, then you might know where this is going. Alright, so we're going to put the dollars over here. And this ratio here, we're going to, since we have the dollar sign up top, we're going to have a dollar sign on bottom. And that's going to cancel out, so we're just going to be left with meters. And usually you like to have whatever unit you want to keep on top. So if we wanted to rewrite this where it's probably a little more intuitive, then we would actually have the meters on top. So we would say that 0.0001 meters equal to $1 bill. And this is going to be equal, as we discussed, to 1.0 times 10 to the -4th. Okay, and so now we're going to put the dollars, the amount of dollars that we have, on the opposite side as this dollar. So since this dollar's on the bottom, we're going to have the dollars on top now to multiply. And then let's see, 4 trillion. Okay, just checking. Alright, so 4 trillion in scientific notation is going to be 4.0 times 10 to the 12th, because that was the little hint that they gave us back here. So 1 trillion is 10 to the 12th. Okay, and we know it's 4.0 because 4 trillion, there's no 4,942 billion, anything like that. So it's just a 4.0. There's no other significant figure after 4. Okay, but if there were other significant figures, they would be after this decimal point, because only the first significant figure is in front of the decimal. Okay, and then we're going to be left with X meters. That's what we're hoping to find out here. So how many meters would that be? How many dollar bills? Okay, so we're gonna cancel this out, and when we're multiplying exponents with significant figures, what you do is you add the exponents. So if you have, let's say you have 2 squared, and you're multiplying that by 2 to the 3rd. Now the base, when you're doing this, the base has to be the same. And in this case, 10 is the base, so that 10 is the same. So in this case, you would have 2, and then the exponent would be 2 plus 3. Alright, so if we're adding these exponents together, then it's going to be negative 4 plus 12, so that's going to be 8. And when we're multiplying these exponents, then we can multiply the bases separately. So 1.0 times 4.0 is going to be 4.0, and then we multiply the base and the exponents. So 10 to the negative 4th times 10 to the 12th is going to be 10 to the 12 minus 4, or 10 to the 8th. Alright, there actually wasn't meters, we were just given X amount of bills. Okay, just saw that there. Alright. So we would have 4 and then 8 zeros after that. So let's answer 4.0 times 10 to the 8th in the answer box. Okay, so 4.0, and let's see. Alright, just checking the format here. Alright, in multiplication, this multiplying is going to be shown by this asterisk sign, so I was just checking to make sure that was right. Alright, so 4.0 times 10, and then the exponent we're going to use this caret sign, which is shift and the number 6. Alright, and then 8. So 4.0 times 10 raised to the 8th. Alright, so we got that right. So in this problem, it shows us that the highest frequency a human can hear has a frequency of 2 times 10 to the 4th cycles per second, and then the speed travels at 330 meters per second. Okay, so we're going to go down over here, and so we have the wavelength equals the speed divided by the frequency, and it gives us that in the problem. Alright, so the speed is 330, and the frequency is 2 times 10 to the 4th. So if we rewrite this numerator into scientific notation, it'll give us 3.30 times 10 squared. And we get that because the the decimal point's over here. So if we're starting at 3.30, that means this decimal place has to move 2 times. So if we have 3.30 and we move this decimal 2 times, that's going to be the same as 330. Okay, so now that we have these in scientific notation, then we can simplify it even more, and let's divide out the numerator and the denominator that are coefficients, and then we're going to tackle these separately. So we have 3.30 divided by 2. So let's do that. 3.3 divided by 2, and that's 1.65. So we have 1.65, and that's going to be multiplied by 10 to something. So we have 10 squared over 10 to the 4th. And there's a few different ways to approach this. Just as you add exponents when you multiply them, you also subtract them when you divide. So you can say 10 squared minus, or divided by 10 to the 4th. That's going to be the same as 10 raised to the 2 minus 4. And another way you can look at this is, I don't know if you know this, but you can switch these exponents around. So if you wanted to move, if you have 1 over 10 to the 4th, that's the same as having 10 raised to the negative 4. So whenever you have a positive exponent in the denominator, that's the same as a negative exponent on top. And if you have a negative exponent in the denominator, that's the same as having a positive exponent on top. So if we were doing that, we'd have 10 to the negative 4th multiplied by 10 squared. And we went over this in the last example. We would add these exponents, so 2 plus negative 4, that gives us the same answer over here, 2 minus 4. So it's going to be 2 to the negative 2. Alright, so 1.65 times 10 to the negative 2. So 1.65 times 10 raised to the negative 2. Alright, so next question. Alright, so in this last problem we have 7 times 10 squared times 8.5 times 10 to the 4th divided by 5 times 10 to the 3rd. Alright, so let's start with simplifying this. So we're going to have, let's combine the numerator and make it 1. So we're going to have 7, we're going to do the coefficients, we're going to do 7 times 8.5, and that's going to be 59.5. Alright, so I just saw that we were short on time, so I just finished up and I'm going to explain it quickly so I don't have to write at the same time. So we're going to combine the coefficients. We get 7 times 8.5 is 59.5. And then we're going to combine the base and the exponent, so 10 squared times 10 to the 4th, and that's going to be 10 times 2 plus 4. And we haven't changed the denominator yet. So that leaves us 59.5 times 10 to the 6 over 5 times 10 to the 3rd. And since scientific notation has to have only one decimal place in front for the first significant figure, so if this decimal place has to move over 1, that's going to be the same as adding 1 over here. So we have 5.95 times 10 to the 7th equals 59.5 times 10 to the 6th. So now we're going to combine these coefficients. So 5.95 divided by 5 is 1.19. And then 10 to the 7th over 10 to the 3rd is the same as 10 to the 7 minus 3, which is 10 to the 4th. So final answer is 1.19 times 10 to the 4th. Alright, so if you have any questions, just let me know.